Hello, welcome to a new video on section 6.4, which is titled Inverse Functions. So in this section, we're going to talk about something new, and it will play a vital role in understanding Chapter 7. So let's start with something simple that you guys are all familiar with. Here we're asked to graph y equals 1/2 x plus 1. So what we're going to do for this one is plot some points, see what happens, and then we're going to do something called the inverse to it. So let's say I plug in 0 for x. Of course, y is 1. If I plug in 1 for x, I get 1.5. 2 for x, I get 2. If I plug in -1 for x, I should get 0.5. And -2 for x, I should get 0. So -2, 0, -1.5, 0, 1, 1, 1.5, and then 2, 2. Okay, so that should seem pretty simple. We'll connect those dots, and here we have a line. Now, let's talk about the inverse. When you switch x and y, that's called the inverse. So let's actually do this in green. So if I switch x and y from the table we just worked out, we have 1, 0. Then, of course, we'll have 1.5 and 1, 2 and 2, 0.5 and -1, and then 0 and -2. So here's 0, -2, 0.5, -1, 1, 0, 2, 2, or sorry, 1.5, 1, and 2, 2. So if I graph that, our line will look like that. Now, here's kind of an essential question. What do you notice between red and green lines? It may not be very obvious, but what if I drew, actually let me erase that one sec. What if I drew that dashed blue line? We would see that the red and green lines are symmetric about the dashed blue line. The equation for dashed blue line would be y equals x. So what happens is that when you have an inverse, original equation and inverse are always reflective about y equals x. Or you could use the word symmetric as well. So if I were to take, if I were to cut out a square piece of paper using this entire coordinate plane, and if I folded it along the dashed blue line, you would see that the red and green lines would exactly map onto each other. So that's kind of the whole concept of an inverse, is that when you switch x and y, we'll see that the equation will be reflective or symmetric about y equals x. Let's do one more, and then we'll end the video. So find an inverse of this. Also graph both original and inverse function. Okay, so you're asked to find the inverse. Now, what do we do in number 1? In number 1, we switched x and y, right? So I'm going to do the same thing here. So f of x equals 3x plus 5. Remember, f of x is like y. So we used a table in the last problem. We made x and y values, switched them, graphed it, and we noticed that y equals x went right through between those two things. Well, algebraically, define inverse you switch x and y. So x equals 3y plus 5. 3y equals x minus 5. Y equals x minus 5 over 3. So let's actually graph this now. So we'll use red for the regular. So 3x minus 5, that's kind of easy. Oops, sorry, I meant to use red. Up 3 over 1. Up 3 over 1. And then for this function, that's like saying y equals 1/3 x minus 5/3. We go up 1 over 3. Make sure I did that right. Oh. Don't you hate when you do that? Originally I had the graph wrong. Let's do this again. 5 up 3 over 1. And I knew I did it wrong because I noticed that y equals x is not going to be symmetric between these two lines. So now let's go green. Okay, that's a lot better now. And you can see that if you were to draw y equals x, it'll go right in between them. So we didn't really need to use a table because we already know how to graph lines. But if you were to make a table for each of these equations, this right here being the original, and this right here being the inverse, you would see that x and y values would be swapped if you actually try making an xy table for each of these. And graphically, we see how they're symmetric about y equals x. Okay, so it looks like we're all set. One last thing. Go Niners. My prediction, SF22, Carolina 20. All right, see you guys after the weekend. Goodbye.